As we'll see in the next theorem, this theorem 2.3 is very similar to a theorem we had about sequences in the last chapter. It says that if we're given a function f from the domain capital D into the reals, and x naught is an accumulation point of the domain, that's our setup for it, I should say. If f has a limit at x naught, then there is some neighborhood of the x naught, which I'm calling capital N sub x naught, and there's a number m, positive number m, such that for every x in that neighborhood that's also in the domain, f of x, the absolute value, is less than or equal to n. That should look like it's bounded. So that's what we're saying. If the limit of the function exists at x naught, then in some region around x naught, some neighborhood, the function is bounded. All right, well, let's look at the proof. It's pretty short. Well, if f has a limit at x0, that's what we're going to assume. Let's call it capital L. Let's let capital L be that limit. And let epsilon equal the number 1, where any positive number would be fine. 1 is just a nice convenient number to pick. Let's let delta greater than 0 be such that the following holds. I'm basically going to use this definition right here. Since this is true, I know this delta exists. X in the domain and x within delta of x naught, but not equal to x naught, implies that f of x minus L in absolute values is less than epsilon, which I'll remind us is 1. So again, why do we know that that delta exists? Because this is true. We know we've defined the limit to be capital L. Actually, another sentence or two and we'll be done. Now we need a capital M. Let M equal the maximum of two expressions. And it'll be clear why I need to do this. It's going to be the maximum of L plus 1 in absolute values, L minus 1 in absolute values, and f of x naught. And that's in the case where if f of x naught exists, if x naught is in the domain of the function. If x naught is not in the domain of the function, then we just remove this third part right here. Okay. So we're going to define our capital M to be this. Notice that's the bound. Capital M is going to be the bound around this little neighborhood of x naught. So I'm going to say, let my neighborhood of x naught, which I need right here to be x naught minus delta, x naught plus delta. And I'll finish it off with a therefore. X in that intersected with the domain again, I'll repeat because it's important. All this theorem is saying is that if the limit exists at a particular point, the function is bounded within some neighborhood of that point. It might have to be a very small neighborhood, but in some neighborhood it will be bounded.